Inverse of a function. All right, this is something that I actually enjoy doing. This is something that hopefully you enjoy doing as well. But anyways, here's the state standards. And to be successful today, you need to be able to explain what inverse functions are, find inverses of linear and nonlinear functions, and determine whether a pair of functions are inverses. All right, so examples of functions and their inverses graphed. The inverse is always a reflection across the y equal x line. The y equal x line is the dotted diagonal line. All right, so again, y equals x. That has a slope of 1 and a y-intercept of 0. So that's just a linear equation. And this is just a line of reflection. When we talk about inverses, it's always going to reflect across that line. So this first graph here, you can see you've got two linear equations. One is the original function and one is the inverse, which is the reflection across that y equal x. The second one is a quadratic function, and you can see that it is the inverse is also a reflection across the y equal x line. Then we have a cubic function, and the cube root function is the inverse of that, and you can see how that is a reflection as well. And then we have the square root function, which is the inverse of half of the quadratic function. So you can see this is a quadratic function, but only for the positive x's, only for x greater than or equal to 0. So it's similar to this, but it's only in that first quadrant. So you're only seeing this first quadrant here. But anyways, I like to visually see those, so hopefully this helps you as well. All right, we do have a couple vocabulary terms. Inverse functions are functions that undo each other. Use the equation solved for x to write the inverse of f by switching x and y. So this is important. This is the way you find an inverse of a function. You simply switch the x and y, and then you solve for the function. So you can see here, if you have ordered pairs in a table or just ordered pairs, you simply switch the x's and the y's, and that is your inverse. If you have a function, like an equation, then you take the x and y and you switch it, and then you solve for y. So these two would be inverses as well. And you can see that the graph of f inverse is a reflection of the graph of f. The line of reflection is y equal x. So you're always going to reflect across that y equals x line, and that's true for all inverses. And this f raised to the -1 power, you don't read that as f to the -1, you read that as f inverse. Anytime you see this in function notation with the little -1, that is the symbol for inverse. You can see up here, it's denoted, inverse function is denoted by f of -1, or it may be g of -1 or h of whatever, but you read that as f inverse, g inverse, h inverse, etc. So I know we've been working with exponents, but in this case, this is the notation for finding the inverse. One-to-one functions, the inverse of a function f is also a function if and only if each input in the domain corresponds to a unique output in the range. Such functions are called one-to-one functions. All right, so the horizontal line test is going to be similar to something you've learned in the past. So if you remember, the vertical line test was how we determined whether a relation was a function or not. So whether a set of ordered pairs, a table, or an equation was a function, we used the vertical line test to see if it would pass at most one point at a time, and if it did, it passed the vertical line test. Well, now we're going to look at the horizontal line test, which is going to help us determine whether the inverse is a function or not. So this one says a function f is a one-to-one function, and the inverse of f is also a function if and only if no horizontal line intersects the graph of f more than once. So we start out with a function. So we're always starting out with f of x, g of x, whatever. We're starting out with a function. So we assume our original equation is a function, or we're given that our original equation is a function, and 1-to-1 means it goes both directions. So this determines whether we have the inverse is a function or not as well. So the horizontal line test, f is a 1-to-1 function if and only if the inverse is a function. So again, if you use that horizontal line test and you move it all the way down across the graph, it only passes one point at a time. That means yes, the inverse is a function. So this one would be 1-to-1. The second example here, f is not a 1-to-1 function because the inverse is not a function. And if you look at the horizontal line test, if you move that horizontal line up and down, that red line, pretend like it moves across that, you're going to see in multiple places, it hits at 2 points at a time. All right, even if it only hit 2 points one time, then it would not pass the horizontal line test. So the horizontal line test helps you see if a function is 1-to-1 by determining whether the inverse is a function or not. All right, so this is brand new information to you, so make sure you kind of read through this until you understand it. Example 1, writing a formula for the input of a function. Let f of x equals 2x plus 3, solve y equals f of x, remember, so solve y for x. Then find the input when the output is -7. All right, so basically when it says solve y for x, that's telling you to switch your x and y, and then you're finding the inverse. But this is just kind of leading us up to it. So it says we've got y, we're going to replace f of x with y, and we're going to have 2x plus 3, and then it says solve for x. So if we're going to solve for x, we're going to subtract 3 from both sides. And then we're going to divide everything by 2. So remember, when you're solving an equation, you're kind of undoing the order of operations. So you're kind of working backwards as far as that goes. All right, so if we solve for x, that is our new equation. And then it says find the input when the output, okay, your output is -7. So find the input when y equals -7. Remember, x is your input, y is your output. So we're going to have x equals, and we have y minus 3 over 2. And then even though this doesn't have parentheses on it, you always are going to simplify fractions by simplifying the numerator or denominator first. So -7 minus 3 is -10 divided by 2. -10 divided by 2 is -5. So when y is -7, x is -5. So your ordered pair would actually be -5, -7, because you always write those as an x and y. So this would be a point on this function. Little side note, it says communicate precisely. The term inverse functions does not refer to a new type of function. The term describes any pair of functions that are inverses. So when you have a function and you have its inverse, those two functions, they kind of undo each other. They're inverses of each other. Example 2, finding the inverse of a linear function. Find the inverse of f of x equals 3x minus 1. All right, so this one's more straightforward. It just says find the inverse. So the first thing we're going to do is write f of x as y equals 3x minus 1. Why do we do that? Because it's easier to switch the x and y. So anytime you're finding the inverse, you're going to switch x and y and then solve. So we're going to rewrite this as x equals 3y minus 1. And then we're going to solve for y. So we're going to add 1 to both sides. So we've got x plus 1 equals 3y. Then we divide by 3. And once we solve for that, that becomes our inverse. So we can write that as f inverse of x. So we've got x plus 1 over 3. So this would be our inverse using inverse notation. And then again here reading, the -1 in f inverse is not an exponent. It indicates that the function is an inverse, not that it is equal to 1 over f of x. So again, this is like a symbol that represents inverse. They're just using the -1 as a symbol for inverse. Example 3, finding the inverse of a quadratic function. Find the inverse of f of x equals x squared for all x is greater than or equal to 0. Then graph the function and its inverse. All right, so we're going to start by rewriting this as y equals x squared. And to find the inverse, we have to switch x and y. So we're going to have x equals y squared, and then solve for y. To solve for y, we have to take the square root to get rid of the squared term. So take the square root of both sides. So we're going to have plus or minus the square root of x equals f inverse of x. All right, so it says to restrict the domain. So we're going to restrict the domain to everything greater than or equal to 0. So we're only going to be looking at the positive square root of x. All right, we don't need the negative since we don't have that. All right, so let's graph this. So we know that the parent quadratic function, we only want greater than or equal to 0, is going to look something like this. And we know the square root function is going to look like this. And then, of course, you've got that dotted line, y equals x here, to represent the reflection line. So, again, we restricted this domain to only the positive values. So this is a poorly drawn graph, but hopefully you get the you get the idea. You can always use your calculator to graph it a little bit more detail. All right, study tip: if the domain of f is instead restricted to x less than or equal to 0, then the inverse is f inverse of x equals negative square root of x. All right, so again, if this had been restricted to x less than or equal to 0, we would have taken the negative square root of x to be the inverse of that. So hopefully that makes sense as well. All right, some more important information again with inverses being new. Want to make sure that we cover this in detail. Inverses of nonlinear functions. So in the previous examples, the inverse of a linear function were also functions. So if you have a line, the inverse of that line is also a function because it's going to pass both the vertical and the horizontal line test. However, inverses of functions are not always functions. The graphs of f of x equals x squared and f of x equals x cubed are shown, along with their reflection in the y equals x. Notice that the inverse of f of x equals x cubed is a function, but the inverse of f of x equals x squared is not a function. So if you take the whole graph here, x squared, remember, is a quadratic function. Here is y equals x, so if you reflect that, you get this image here. And so that would not be a function. So to make it a function, that's why you would restrict it to only positive numbers, only non-negative real numbers. So when the domain of f of x equals x squared is restricted to only non-negative real numbers, the inverse of f is a function as shown in the example. So the example that we just did, it says the next example, but the example that we just did, we restricted the domain to only x greater than or equal to 0, which would have been this half of the graph, and this would have been square root of positive x only. So basically what this is saying is sometimes they're going to put a restriction on the domain to make sure that it is a function. But there are cases where if the domain is not restricted, then you may have an inverse that is not a function.